Hey guys, so today we are going to talk about the molecular orbital theory, which is another way to explain how molecules and how their geometry is affected by the distribution of electrons. Now, before this, if you haven't checked out the VSEPR and the VBT, I'll leave the links down below so that you can check them out as well. Now, so we know when atoms approach each other during bond formation, that approach changes the way the electrons are distributed, right? Now, electrons being very small particles can be imagined as a wave or a particle. It has dual nature, right? So let's understand, let's imagine the waves as like this, right? Like two sine waves. Now there's, about waves, when they can interact in two possible ways. They can interact in phase. Now when they interact in phase, that means what will happen is the resultant amplitude would be larger. As you can see, the amplitude here has grown, right? That means we have greater probability of finding electrons, right? We have greater probability of finding electrons when we have in phase, right? So places where we have in phase, there we call these such orbitals as bonding orbitals. The energy here will be lower. Why? Because the probability of electron is high and hence the repulsion between the nuclei would be less. Now there's another way in which the interaction can happen, and that is out phase. Now when the interaction happens in the out phase manner, what you will see is a flat line. Why? That means there is very reduced or very less probability that you will find the electrons in this position, right? So you have in phase and out phase interactions. The orbitals formed as a result are called as anti-bonding orbitals. Now as you can understand that this is the type of orbital which will have a higher energy level, right? So we represent the anti-bonding orbitals and bonding orbitals with a difference. So let's say 1s, two 1s orbitals combine, two 1s orbitals combine, so they may form in phase, they may interact in phase, or they may interact out phase. So when they interact in phase, they may form bonding orbitals and anti-bondings. So I'll write sigma 1s to represent the bonding orbitals. Now you have to understand, when I represent this diagram, I'm assuming the y-axis to represent energy, right? So it's never drawn, but horizontal scale represents energy. So that is why the sigma 1s, the bonding orbital, is drawn on the lower end, right? Whereas the sigma 1s star, this star mark represents the anti-bonding orbital. Now you must be wondering, why did I use the word sigma, right? Now if you remember the past videos in the VBT, that is Valence Bond Theory, you'd understand that bonds could be of two types. I'll leave a link below for you to understand the sigma and pi bonds. I hope you remember the difference. Sigma is when the electron cloud is oriented cylindrically in the direction of the bond, right? Whereas pi bond is not cylindrical, rather parallel or perpendicular, right? So that's the difference between sigma and pi bonds, and I hope you remember that. If the P, remember the p orbitals, we have px, py and pz, right? So px orbitals, they will interact head on, right, whereas py would be parallel to each other as well as pz, right? So that is why so those pz and py would form the pi bonds. So here we just have one s sigma bonding orbital and one s sigma star antibonding orbital. So this is what the molecular orbital theory wants to explain. Let us do that for hydrogen. Now, I think it's very easy. Why? Hydrogen H2. So we have one orbitals, one orbital each in this case, and both of them are carrying just one electrons, right? So what we do is we draw boxes here. So what is this box here? It's sigma 1s. This is sigma star 1s, right? You add the boxes and you fill one electron here and one electron here, because each of them just had one electron each. Now, you have to keep in mind three rules that you must obey while you are filling these orbitals. And what are the three rules? We have already covered these three rules, but it's better to remember them. The first one is off-bow. Off-bow says that the lowest energy level would be filled first, right? Lowest energy level would be filled first. Pauli's exclusion principle says that you can have a maximum of 2 electrons in a particular orbital, not more than that. And finally, we have Hund's rule. Now, what does Hund's rule say? That electrons must occupy all orbitals of the same energy. First, all orbitals of same energy must be occupied before, right, before you can enable the pairing, right? So these are the three rules which you must keep in mind before you draw electrons here. Now, you can use the same basic stem to draw other molecules. What I am going to do is, let's try to pull in the electrons together in tabular format. So here I have written a few diatomic species starting from hydrogen till oxygen, and what we'll do is we'll fill the electrons by using the three principles we just talked about: off-bow, Pauli and exclusion. So H2, remember 1 plus 1, right? 1 electron each. So this is how it goes here. In case of S2, helium has 2 plus 2, 4. So first I'll fill these two, and then I'll go on to the next energy level, that is these two. Lithium, again 3 plus 3. So this is how we are going to do. Now, if you're wondering that this is just a filling exercise, things would start to make difference very soon. So beryllium 4 plus 4. So I'm going to simply pull here. So sigma, sigma star, sigma, sigma star. So first 1s, 1s, then 2s. Now things become a little more difficult or when p comes in. Now I hope you remember we just talked about that the p orbital will have three orientations. So we'll have sigma in px, whereas pi bonds would be formed in case of py and pz, right? Now both pi bonds would carry lower energy. As you can see here, the pi bonds are carrying lower energy than sigma bonds, right? This is for bonding, right? Now understand carefully here that the red here represents anti-bonding. That is why they are written above, right? Now, so let's again return back to our task, that is filling in. So boron is 10, right? So I'm gonna first quickly fill the 8. Now remember the Hund's rule says, Aufbau says lowest first, exclusion says that you would have only 2 electrons in any given orbitals, but Hund's rule says that you have to pair only once all orbitals are singly occupied. So you have 2p pi 2py and pi 2pz. So you have to first fill both of them singly, right? So this is what I am going to do first, right? Then I am going to pair, but we only have 10 electrons. So as you can see here, let me use another line to make sure that you understand that you have 2 orbitals here, right? So these are singly occupied. That means they will be paramagnetic. Now, this is one of the triumphs of molecular orbital theory, that it is able to explain why oxygen is paramagnetic. We observe in field that oxygen is paramagnetic. Oxygen 8 times 2, that's 16. Now, if you see carefully, then we have total 16 electrons for oxygen, and here again you have to fill them singularly first. Now, this is one of the triumphs of molecular orbital theory, right? I hope this makes sense. If you have any questions, leave it down in the comments. I'd be more than happy to answer them.
We hope you like this video. Press subscribe, thumbs up, and stay geekly.